All right, welcome to 50 Shades of Caching and how LLMs painted black. Before we start, it's important to say that views here are my own and not my employer's, which is the Wikimedia Foundation, the nonprofit running Wikipedia's infrastructure for the past 22 years. Wikipedia is a free encyclopedia where all content is free and managed by volunteers. We support 300 languages. It's 25 years old, and it has been trained in LLMs since they were just called statistics. Also, every visitor gets exactly the same content, regardless of who they are or where they're from. And we do host some really extraordinary stuff, shaped by what matters and what's happening in the world, like during major global events like the 2014 Ebola outbreak, or the COVID-19 pandemic, where relevant articles were completely overhauled and translated into hundreds of languages. And that is the power of the global community. From pandemics to biographies of important people, to scientific articles, to interesting essays, to political articles. But finally, a definitive answer as to who is the real queen of pop. So Wikipedia says Lady Gaga, my dress says otherwise. We have the same tailor. Now, speaking of royalty, we now know who the real king is as well. Or, if you cannot be bothered with all that, you can just click on the personal life section of your favorite supervillain. So, at the same time, besides Wikipedia, the Foundation hosts a number of equally important and interesting projects like Wikicode, Wikiversity, Wikisource, and of course, Wikidata. Hi, I'm Effie. I used to sell encyclopedias at small shops before joining the Foundation as an encyclopedia reliability engineer. I've also got a degree in physics, which is a very handy excuse of saying, this is a fascinating problem, I have no idea what's going on, I just studied physics. Thank you for coming. And let's crack on with caching, while I try to sell you some encyclopedias along the way. According to Wikipedia, caching is a hardware or software component that stores data so that future requests for that data can be served faster. And caching is everywhere, like your CPU, page caches, database caching queries, CDNs caching content closer to the users, your own browser is caching, but also, whether we realize it or not, caching is part of our daily lives, right? You stick a Post-it with your Wi-Fi password on your fridge for your guests, and another one with your Netflix password on your mom's fridge, along with a tweet that didn't age very, very well. Now, caching is not just about sticky notes and shared passwords. It is giving us some of the nastiest security bugs in the industry, the kind that slow down our processes, albeit with the best logos in tech history. I mean, for a while, security researchers were all the rage, looking cooler than the rest of us. Greatest hits are Meltdown, affecting many Intel CPUs, allowing attackers to read arbitrary memory. Spectre, tricking the CPU into fetching data it's not supposed to. Foreshadow, leaking data from the L1 cache, and even across virtual machine boundaries. Zombie load, spilling tiny pieces of dead data. Cache out, letting attackers read data that has been evicted. Not pictured, due to poor marketing. Cloud bleed, leaking chunks of memory into cached responses to random users. And honorable mention, not a cache bug per se, Heartbleed, because it was spitting cache secrets. Now, fancy logos aside, in the same way we know our behavior and we decide what to cache and where, caching systems are optimized to improve performance by analyzing human behavior. Now, quick word about this talk. Number one, I will be using examples from the Foundation, from our infrastructure, and I will be simplifying a few things here and there, which means that I'm trading accuracy for clarity. And when I say we, usually I will mean as websites providing content, though at times I will mean Wikimedia. Moving on, here's what we'll be covering today. We'll go through the caching layers one by one, from your browser all the way to the content delivery, and content delivery networks and applications. And next, we'll discuss how we keep that fresh, or at least fresh enough. And finally, we'll see how AI organizations take all this clever engineering and just politely toss it in the bin. Let's start the story. I promised I would keep things quite simple, and I really meant it. This is a bit of a really boring technology, which will be our guinea pig for the rest of this talk. It is just an Apache PHP MySQL website about ducks. And according to the internet, this is also how Wikipedia works, and you can run it from your laptop. Which brings us to the CDN chapter. Before we get into CDNs, we need to do some caching, web caching basics. Web caches are not a proper term, probably, but let's go with it. There are two kinds, public and private. Private caches are basically your browser, and other caches are public. Could be a proxy of yours, could be your organization's big brother, could be a CDN. By and large, caches use URLs along with various parameters as keys. So two identical URLs with different parameters are treated as separate entries. These parameters often come from the URL itself and from HTTP headers, such as accept encoding or user agent. If we are variant by user agent, which means mobile versus desktop, these headers determine which version of the site will be caching. Moving on to cache control headers, define how the response should be cached, and by whom, private versus public. And finally, cache validation headers are used to check whether the cached responses are good for how long they are fresh. Moving on to a sample key entry, we have a key which includes, this is the kind of the key value database your browser keeps, right? And it has parameters that just like the ones we mentioned. Furthermore, we have response headers, the actual body, and metadata, like when this URL was cached or when it expires. So in a way, we can say that a web cache is just a pile of URL responses with metadata pretending to be organized. And now on to a couple of more examples. This is a request to the English Wikipedia logo, which does not change very, very often, as we know. Date says when this response was generated. Expires and max age tell us how long this is good for. So this is good for another year. Next time my browser requests this, because of cache control, it's going to treat that object as fresh, and it will just fetch it from its local cache without even asking. eTag and last modified are backup validators for when this object has expired. In this slide is another example, but this time is for JavaScript, for a JavaScript script. The cache control headers here have a max age of 600, max age 600 again. This is the private caches and the public caches. That's 10 minutes. But what does the stale while revalidate mean? Minute 9, the cache is fresh. Minute 11, the cache is 1 minute after its expiration. So the browser will serve the stale content, but it will try to revalidate from the origin. So by minute 12, we have fresh content. And save the best for last, this is a request to a wiki article. We again have date, last modified when the resource was changed. And the server name here is the Kubernetes pod, which is the name of the pod that actually rendered this content. And this time we have cache control says private, max age 0, must revalidate. This is a way to politely tell the browser to cache it, but ask before using it again. So next time we do a request like that, the browser will send a header saying if modify since. So then the server will respond with 304 not modified. Having covered the caching basics, we move to the CDNs. As you probably know, CDNs sit between DUCs and backend servers. But why do we need them so desperately? Speedy delivery. Pages load faster because static content is delivered closer to the user. Some CDNs even go a bit further, and they predict what the user is going to fetch next. They do some sort of routing, like you being routed to the nearest CDN. They offer reliability. As you can imagine, a CDN is not just one server. And the more cacheable content we have, the less load we have on the origin. They also add security. CDN can perform TLS termination for you, DDoS protection, absorbs bad traffic, and they can help protect your network and transport layers as well. And lastly, during high demands, they can protect the origin servers with various load shedding methods. Right, enough theory. This is the Wikimedia CDN and how it looks like on the map. We have 2 primary data centers in the United States, in Texas, in Austin and Virginia, where all the actual content is stored. And we have 5 caching points, 2 in Americas, 2 in Europe, and 1 in Asia. Right, this is how it looks from a Duck perspective. It's our simple, boring infrastructure again. Zooming into the CDN itself, we expect to find a bunch of cache servers located across the world. Which brings us to what is in a cache server. I can speak about our cache servers, obviously. And we have a few HTTP layers. There are layers of HTTP's proxies. The outer layer is HA proxy, responsible for TLS termination, HTTP2, throttling, rate limiting, the lot. And then we have varnish, caching objects in memory, where all the frequently accessed stuff lives. Thus, it's doing most of the heavy lifting. And lastly, the ATS layer, the Apache traffic server, storing objects this time on disk. Those 3 services coexist within the same cache server, bare metal in our case as well. 2 things to note here as well. There's a lot of routing logic in the services that we're not covering today, obviously, and each caching point, each point of presence, has 2 sets of caching hosts. One dedicated to text, so this is like JavaScript, CSS, HTML, and we call them text. And the other one is dedicated to media, which we call upload. Images, videos, load. Before we conclude the CDN chapter, there are a few fun facts that I really like. Zipf's law is an empirical observation saying that your most popular item is twice as popular as your second one. So if we're hosting a pictures of 100 animals, the dog has 20 hits per second versus the cat that has 10. The outcome of Zipf's law is a Pareto distribution, which says that 80% of your traffic comes from 20% of your content. So 20 animals will be generating most of our traffic. Now, maybe in some parts of the world, dingoes are more popular than dogs. So caches have regional content characteristics. And lastly, paid CDN services may also have to enforce privacy laws, block content due to licensing or censorship reasons, etc. Right. Caching header's done, CDN's done. You can interview for Cloudflare now. And if any of that sounded Greek, we're in Athens, it tracks. Let's head deeper into the rabbit hole. So far, our Duck website has reduced the network reaching our backend servers with the magic power of browser caching and CDNs. But we cannot do that forever. Things are changing. Our Linux, Apache, MySQL, PHP website is a very vibrant place. Articles are added, they are deleted, so we have cache misses, we have cache revalidations, and requests landing to our backends, which at times might stress the backend or the database. So we have to add some more layers of caching there, which is the application caching. Application caches broadly fall into 2 categories, in-memory and external. In-memory lives inside the application itself, so in the application process itself, so it's RAM, it's very fast, but limited to what the process, with the memory that the process has, and everything is lost when the application restarts. External caches sit outside the process in a separate data store. More resilient, larger data sets, they can be shared across multiple applications or applications instances, and typical examples are Redis and Memcached. Next, we will discuss the PHP in-process memory caches and one external one, Memcached. I know everybody likes the PHP crash course, So for the rest part of this section, I'm afraid you're going to learn a little bit more about PHP than you bargained for. There was even a talk yesterday about PHP being dead, so this is officially a lesson of history. So PHP FPM is the process manager for PHP. It manages a pool of workers and uses shared memory. Through shared memory extensions, those workers can share data between them. PHP, loosely speaking again, has two in-memory caches. The first one is op cache. It stores compiled PHP code, PHP bytecode in memory, and it's not something that we can directly access. And it just sits there making things faster. The second one is APCU, the user data cache. This is a key-value memory that store that developers can actually read from and write to. Following the really boring life of a PHP request, historical journey as well, when a user initializes a request, it's first received by the web server, be that Nginx-, be that Apache. The web server forwards this to PHP FPM. FPM delegates that to the Zend engine, which is a PHP runtime, and the Zend engine analyzes and compiles the PHP code into opcodes. Opcodes are stored in op cache and then executed. During execution, the script might fetch data from APCU. Usually, you can find stuff there such as counter lists, configuration settings, variables, the lot. And developers there have to explicitly do APCU store and APCU fetch. Of course, similar caches exist in other languages, and here are some examples in Ruby and Java. Furthermore, if the script requires data, PHP queries a database, renders the HTML, and transmits the response back to the user through the web server. Moving forward, and this is the last time you will see that, I promise, we are going to add some external caching in the mix. So during execution, we may attempt to fetch data from an external cache before querying the database. Our external cache example here will be memcached. I don't need to sell memcache to everyone, but it's worth mentioning, covering the high-level stuff that makes it one of the building blocks of the internet. At its core, memcached is just a key-value in-memory store. It lives entirely on RAM, though we can push colder data to disk using xstore. To reduce memory waste and fragmentation, it divides the memory into fixed-size slabs, where each slab class has objects of similar size. It's LRU, meaning it treats data as hot, warm, cold, and evicts them. And we use memcache to sort all sorts of ephemeral data, article metadata, fully rendered pages, the lot. The lead developer is Dormando, and it's genuinely an amazing piece of software. The kind that when it breaks, it's not memcached, it's you. And zooming out, we see memcached pools, each pool made up of multiple nodes. So even though memcached data are considered ephemeral, that does not mean that the service shouldn't be reliable. Every cache hit is work that we do not have to do in the backend. Now, memcache has not always been distributed. Recent versions do ship with the built-in proxy, but historically, if you wanted distributed memcache, you needed a proxy in front of it. So MacRouter enters the chat. MacRouter is a transparent memcached proxy and router open-sourced by Facebook. Its main feature is advanced routing, including sharding, replication, all the things we want. It applies consistent caching, so each key ends up in the same server, on the same node, and it supports failover. So if nodes are dead, there's a failover pool to take over. It also provides prefix routing, so developers can add prefix specific keys when MacRouter will write them to specific servers, or you can use the same pool of servers for different applications. But most of all, it is battle-tested, and it scales easily. It has been serving us very, very well at Wikimedia for many years, and for us, it is millions of requests per second. At Facebook, it's like billions of requests per second. So MacRouter sits between our PHP processes and our memcache servers. For the Kubernetes buffs, at Wikimedia, MacRouter runs as a daemon set in our Kubernetes cluster, where we host also our media wiki pods, the application. So from the application's perspective, this is just an address, a single memcached server. And this is exactly how I broke infrastructure, twice, as one does. The first time it was DNS, and I'm sorry for not getting into many, many details here. The gist is that we switched all MediaWiki instances to use a single answer and single address that would, in theory, route them to the nearest Mac router instance. But sadly, this led to tens of thousands of requests, and our internal DNS server crashed. The reason was kind of elementary, my dear Watson. So for those not privy to DNS stuff, a trailing dot here signals that this is absolute. Stop querying the DNS for the various search domains that you may have. The second time, surprisingly, it was not DNS. I simply wired the MediaWiki to an address no one was listening to. And the database folks were not very impressed with that. There are postmortems for both incidents. But just like many good things in life, stuff go from fresh to stale. And so just like cache freshness, this will be a short chapter. So once upon a time, our cache was fresh. Via lazy loading on a cache mess by fetching data from the origin, be that a database, be that a backend server, be that our rubber duck wiki. Or right through. After an update, our application updates the relevant cache entry synchronously, or by simply pre-warming, because someone or something decides that we need to proactively refresh the cache. Meanwhile, there are also many ways to invalidate based on your needs and your optimism. As a rule of thumb, it's usually cheaper to let caches expire than to invalidate or delete them yourself. So the usual strategies, we know that more or less. Time to live, expire after a fixed time. Write around, update only on the backend, and cache them on the next read. Write back, cache first, tell the backend later. Manual, explicitly clear caches via an API call, for instance. Versioning, which is quite interesting. We keep versions of keys and bump it in case of changes. So this will cause a cache mess in the next read. And the very handy event-driven, where an app emits events to invalidate caches. Super useful when we have many caching layers, multi-tiered caches to say it more properly. In a nutshell, browsers and CDNs cache responses for URLs. Application layer caches store the data needed to build those responses. Right. Bear with me, this is the last chapter. This section was the hardest one to write because we are all still coming to terms with our feelings about AI. Nothing particularly deep here or new, I'm afraid, but if LLM scrapers is not a conversation that comes up at work, I really hope you're enjoying the peace of quiet. Other than that, this section raises more questions than answers, and it affects all the content providers. Everything we have covered so far is a really, really, really long version of saying that we have optimized our systems for human traffic. Yay! As users, we surf the internet and in a roughly similar manner. Like we scroll down, we click on things, we click on pause, we click back. And they're all predictable. To top it up, as content providers, we budget our capacity for human behavior. We plan for traffic spikes. We plan for the odd major news events. And at Wikimedia, the latest PayPal announcement last year broke our all-time records. Traffic peaked at 800,000 requests per second. That's 6 times our normal traffic. And egress bandwidth hit 134 gigabits per second, twice the normal traffic. And we survived that, which is a proof that we built our systems to bend when the circumstances demand more, but not to break. Right. In the olden days, by which I mean, 2 years ago, when we saw odd traffic anomalies, that were not linked to any ongoing event, they were usually easy to pin down. And some of them were genuinely funny, like an image of a flower hitting 90 million hits a day because a mobile app got pushed in India and someone copy-pasted code from Stack Overflow. Or a PhD student who did not quite understand request concurrency. But since January 2024, we have seen 50% increase in bandwidth usage, mostly used by bots. No famous people dying, no breaking news, no users, just bots. Which means that the rise of the machine nowadays are human-operated robots, which are a mix of things, most notably LLM training, testing and benchmarking, AI agents and chatbots browsing on behalf of humans. This is an example of a pattern that we see more often than we would like. A traffic spike between a caching point and our primary data center, jumping from about 200 megabytes per second to 6 gigabytes per second, which is frankly a bit much. This is to visualize in the map that this is data coming from the US to Europe because someone's requesting that content from Europe. And while this is almost certainly the work of a single actor, if we try to zoom in into that traffic, we will see countless user agents, we will see countless IPs, and multiple countries of origins. So why is that a problem? This MO that we see quite often exhausts our cross-data center links. And this is not the volume of traffic that we would normally budget for. Now, not this one specifically, but we've seen worse. But on top of that, this is putting real pressure on our origin media servers, which need to serve real, legitimate traffic. And the problem with all that is pace. There's a whole AI economy which is growing faster than we can imagine, and they're hoovering the internet like nobody's business, unpredictably and scraping horizontally, all at once, and not following existing standards or rules. I almost never put memes on my slides, but I will make an exception. Because this one hits the nail on the head. You had the API consumer, and you have all those rules so they can behave well, and then you have the scraper who just does everything. This is very popular at work right now. So what is also interesting to mention is that they are trying hard to pretend they are something else. They impersonate the Google bot. They impersonate other LLMs or AI agents. And they're trying super hard to pretend to impersonate humans. So residential proxies are the new Blαck. For those not aware, residential proxies route traffic through ordinary residential internet connections, which is pretty shady, as it is often unclear if the user gave consent for that, while installing this free VPN extension or while downloading this free, something mobile game. And no, they never read the fine print. Mind you, we're not the only ones facing this, right? Which brings us to the fun part. Who is actually paying for all that LLM training? And that's everyone. News sites, media outlets, code review platforms, even 90s GeoCities pages that somehow survived. And how are we paying? Well, traffic costs, compute costs, power consumption, monitoring fatigue, playing whack-a-mole with the next bot that is exhausting your links. And that's not the AI companies, this is everyone else. The uncomfortable bit is that content providers, we used to plan on the basis that, say, 99% of our traffic was cached. And we could tolerate the occasional slow query, slow request, cache misses, the person looking at a forgotten article. But if the efficiency has dropped to 80% now, this might mean that our users are not getting the service that they are used to. So, let's cache everything. Great idea. Dynamic responses, URL parameters might change the rendering of a page. And each page exists in multiple formats: gzipped, uncompressed, mobile, desktop, different languages, different locals. So we're not caching one thing, but rather we are caching many variants of the same thing. And it does not stop there. Data is constantly changing, So we have invalidating, warming up, and if we put now cache regionality in the mix, it will feel like having shops in Italy baking every day fresh Hawaiian pizzas just because some tourist might turn up and ask for one. It's a complete waste of, waste of pizza, pineapple, and many angry Italians. So, can we strike back? It was very hard to find this poster. This is capitalism. So, where there are problems, there's usually a product category. And this one here, fundamentally, is charging people to tell one robot from the other. We now have IP reputation services, cloud providers and application firewalls, firewall vendors selling anti-crawler tooling and protection. CAPTCHAs have been around forever. They're doing browser-level checks. And they have added now J3 and J4 fingerprinting, which identifies clients through their TLS and HTTP handshakes, with using things like cipher suits, number of headers, etc. All great ways to separate real browsers from Python scripts. All great places to apply machine learning. And that said, sometimes the tooling gets it slightly wrong, and a website might end up accidentally block your browser. Sorry about that. But is there a way out of this? We can't. First of all, it's not every single AI company that is bad, okay? I mean, especially the big players, they have trained their models. But we can't play defense forever, and we cannot keep crying over spilled bandwidth, and we can't keep banning one bot after the other one. Bots will be eventually trained, models will be eventually trained, and the quality of the sources does matter. We are entering an era where people will not get their information from primary sources, but from chatbots. And just like people believe what someone said on the internet, they will believe what a bot said to them. And luckily, there are a few ideas around. They're still emerging. We'll see. First, improve performance. Caching has been covering for us sins for quite a long time. Now that more traffic is hitting the uncached path, slow path matters again. We should probably get better at it, and frankly, maybe we should have been doing that all along. Second, serve cheaper content. Rendering full HTML pages is costly for the servers, but it's also costly for the consumers, the bots that are trying to render the HTML page and consume it. Both sides lose. Markdown is cheaper, and there's even an RFC for it. Third, LLMs.txt. This is an emerging equivalent of robots.txt, but aimed at AI crawlers, as a way of sites to say that here's what you can have and here's what you can't have. Bear in mind, this will work for honest robots too. And lastly, making website snapshots a standard. Instead of crawlers grinding through page by page by page, just publish a snapshot. And a structured dump of your content updated sensibly. Honestly, it will be okay. We've been there before. Relentless crawling is not actually something new. We have had spiders crawling the web since the 90s. Search engines were racing to index everything, believing they would be like the next Google. And for a while, it was genuine chaos. But eventually, a rough balance was found. Crawlers became more respectful. Many people, companies decided they can't beat Google. Operators got better at managing them. Indexing turned into a more or less civilized thing. And now, the AI slope right now is a bit of a circus. But the monopoly money currently funding AI will eventually dry up. Products and companies will mature, standards will settle, and the dust will settle with them. It just needs a wee bit of time. Now, we've said lots of things today. You're a very brave audience. This is the end of the conference. But what is the takeaway? So the Terminator was wrong. Skynet is not coming to end the world. It's going to scrape the world until it runs out of monopoly money. In the meantime, we have automated both sides of this battle. We have robots deciding whether the thing on the other side is a robot or a robot pretending to be a human or a human in a trench coat. So if there's a fight of robots against robots, why are we still getting paged? Thank you. That's the talk.